Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 1, Part C. Question 1 for Part C is derive the system of ODEs that describe the time-varying concentration of N-stirred tanks in series. So to do this, I'm going to start by drawing a picture to better understand the situation. So the question says we have a series of CSTRs. So we're just going to draw a couple. There's 1, 2, 3, 4. Of course, there are stir. There's some amount of liquid in the tanks. So we'll have our Q flow going into the first tank, it goes into the second, the third, the fourth, and finally out the bottom. So for our first tank, we'll have our concentration in, and we'll have the concentration coming out of this tank. So we'll call this tank 0, 1, 2, this is tank N. And coming out of the first tank, we'll have concentration 1, 2, eventually concentration N for our nth tank. So to derive our equations, we'll start with our tank 0, since this has a special equation for it. So if we want to know the concentration in the tank, so it's changing with time, we'll have V dc0 over dt, and this is just going to be equal to the flow in minus flow out. So that's our Q, and our concentration in is going to be in minus the flow out, so Q minus the concentration going out of tank 0. Then for tanks 1 through N, we have another differential equation. I'm going to write it out in terms of our tank 1, but you'll be able to apply the same equation for tanks 1 through N. So we start with the same thing. Concentration in tank 1, so C1 this time, dt is equal to U times the flow from the previous tank, so it was coming out of tank 0, minus the flow coming out of the first tank, which is C1. So if we wanted to continue this on, you would have your flow in being what was coming out of the previous tank minus the flow going out of your current tank. You would just kind of apply that for however many tanks you have. Now to isolate our derivative on the left-hand side, we're going to divide both sides by V. We do this for both equations. So dc0 over dt is equal to Q over V times C in minus C naught. And for this equation, we have dc1 over dt equal to Q over V times C naught is C1. There we have our two differential equations for that flow through a series of tanks, and number of tanks. We are ready to move on to question 2 of Part C. This states that for a total volume 1 liter distributed over 20 tanks in series in a flow rate of 0.1 liters per second at steady state with a concentration of 0.1 m flowing through the system, a rectangular pulse of concentration 0.5 m enters the first tank at 1 second and reverts back to 1 m at 2 seconds. Modeling the boundaries of this rectangular pulse as a scaled / time-shifted sigmoid function with width scaling of 50, simulate the response of the system. In particular, show A plot of the time-varying concentration, just x-axis is time, of the 20 tanks, and B, plot the concentration profiles, which is x-axis is the fractional traversal across the 20 tanks ranging from 0 to 1 at varying times. So to do this, we can head on over to Google Colab, where as usual we're going to start by importing the libraries that we need. We import NumPy as NP from scipy.integrate, import solve underscore IEP from subplots, import make subplots from scipy.special, import exp. Now we need to enter our parameters. So we have our volume is equal to 1 liter, n is equal to the number of tanks, it's 20. This volume here is actually our total volume, and if we want the volume of each individual tank, we need to take the total volume and divide by the number of tanks. We know that the initial concentration is 0.1 m, and we know that the flow rate is 0.1 liters per second. Now we also want to establish the initial concentration of each individual tank. So C naught is equal to P dot full. And so the number that we have is N. We want to set it to the initial concentration, just CA naught. Now that we have that established, we can start defining our functions. We can define the right-hand side of our equations. Our independent variable is time, and our dependent variable is concentration. And the equations we want to set up here are those ODEs that we established in part 1. So we have dC0 is equal to Q over V times concentration in, which is going to be a function of time since it's changing, minus the concentration leaving tank 0. Now for our differential equation for our derivative for tank 1 through tank n, we have Q over V times the concentration of what's coming out of the previous tank. So we're going to start with that 0 tank and go all the way through the second to last tank. And I'm going to subtract by the concentration leaving each tank. So we want to start with the concentration of tank 1 through n tanks. I'm going to return, but we want to combine the results of these differential equations. So we're going to do np.row underscore, so this is row concatenation, and we're just going to do this not C1 n. Now of course we still need to set up this function here. So we're going to define in time, and we're going to return our results. Now for this is where we're going to see that pulse. So at time 1, we see it go from 0.1 up to 0.5. So to do this, we can use our exp function. So we have 0.1, which is where we started, plus 0.4 times exp. And for our scale, we have 50. So we're going to do 50 times our t. We're going to subtract by 1 since this happens at t is equal to 1. And now this is where our concentration increases, but we also know that it reverts back down. So we're going to subtract to show that. Instead of at time 1, it's at time 2. Now that that is all set up, we are ready to plot and kind of get a visual and make sure that this is working as we expect it to. So we can do t plot is equal to np dot line space 0, 10, 200. I'm going to establish a figure. So we make underscore subplots, and then we're going to get scatter. So our x-axis is t plot. Our y-axis is cn t plot, and our mode is going to be lines. And then we're just going to update the layout, have a better visual on it. So we have a width is equal to 800 and height is equal to 400. And there we can see the pulse that goes from point 1 to point 5, spanning over T1 to T2. Now that we have this established and we know that our model is working correctly so far, we can move on to plotting this with concentration versus time on the x-axis. First thing we need to do this is do our solve IVP. And for this, we know we're going to need a t end, so we're going to put that at 50. And we have res is equal to solve underscore p. Our function is our right hand side. Our time is 0 to t end. Our initial guess is c naught. Our method is do need dense underscore output equal to true. Now we are ready to plot this, so we need to do t plot equal to np dot in space 0 to n 100. Then we're going to seize, these are our concentrations of each tank, res dot equal to plot. Now we can do our second figure, make underscore subplots. Now we're going to make a loop so that we can do this calculation for each tank. So we're going to use enumerate, seize, so figure 2, add, scatter. Our x-axis is t-plot, the y is concentration, we want lines, we want to name each line, so we're going to do tank, and then whichever iteration it is. Okay. And we're just going to update the layout so we can see it a little bit better, as usual. There we go. Now we have our graph with our time on the x-axis and our concentration here, and we can see how this pulse affected the concentration in each of the tanks. Finally, we are ready to plot this series of reactors as position on the x-axis versus concentration on the y. So to start, we want to establish our x-plot, since instead of t on the x-axis, we're going to have position. So we go from 0 to 1 times. Make our third figure, so make underscore subplots. We're going to make another loop. This time it's going to be for I in range 200 in increments of 10. Going to make a scatter plot. Our x-axis this time, like I said, is x plot instead of t plot. Our y is concentrations, and it's going to be from the beginning to the current iteration. Mode, again, is lines. And we're going to name each line with the time of whichever iteration we're on. Each iteration, like since we're in increments of 10, we aren't going to quite make it to 200. It's going to stop before that. So we're going to copy paste this and make a separate line for just the last tank. So instead of going to I, it's going to go to the last tank. So we're going to put it as -1, and we're going to call it times 200. Finally, we're just going to update the layout. Just enter. Get rid of that together. A million typos. Let's see. Make sure these are 3. There we go. Finally, we have our answer where we can see how the position or the concentration changed in reference to the position instead of the time.